Hello everyone, my name is Zhang Yichen from National University of Defense Technology, Changsha, China. The title of my paper is Memory-Aware Optimization for Sequences of Sparse Matrix Vector Multiplications. First, I will introduce motivations of this paper. Before we talk about sequences of SPMV, let's start with familiar SPMV, which is sparse matrix vector multiplication. An SPMV operation multiplies a sparse matrix A by a dense vector X and then produces a dense vector Y. SPMV is characterized by a low arithmetic intensity and irregular memory access patterns. So it's often responsible for the performance bottleneck. Efforts have been made to enhance the performance of SPMV by optimizing the storage format and the competition kernel. These prior works have primarily focused on the computation of a single isolated SPMV invocation. While important, they ignore the optimization opportunities for a sequence of SPMV operations, which is double SPMV. A double SPMV pattern involves performing a series of SPMV operations, such as AX, a to the 2 power times x, and a to the k power times x, and their linear combinations, such as a to the 2 power times x plus ax. And note that the same sparse matrix A is reused across invocations. Double SPMV is commonly seen in solving eigenvalue problems, linear equations, and multigrid methods that underpin various scientific applications. Given the importance of double SPMV in scientific computing, there is a critical need to identify optimization opportunities. In this paper, we introduce a new approach for optimizing double SPMV by leveraging the sparse matrix data locality across consecutive SPMV invocations. Our approach involves revising the classical double SPMV computation pipeline used by mainstream algorithm to reduce the number of data accesses to the sparse matrix A. Specifically, our paper will take MPK, the sparse matrix vector power kernel, as an example, which calculates a to the k power times x. In this part, we use the MPK method as a working example to explain our solutions. Figure A outlines the processing pipeline of the standard MPK, which computes the result by multiplying sparse matrix A with the outcome of previous SPMV invocations. It requires k memory access to matrix A when computing a to the k power times x. Figure B is our proposed processing pipeline, namely forward and backward MPK, FV MPK, by splitting sparse matrix A into submatrix L, U, and D. An SPMV operation is translated into computing the sum of 3 terms, and note that we ignore the representation of the diagonal matrix D because it's quite simple. We compute XL and XU in the forward and the backward stages, respectively. We access submatrix L from top to bottom in forward stage, and access submatrix U from bottom to top in backward stage. Except for head and tail, we will perform 2 calculations every time we access an element of the submatrix. This means that when k is large enough, the number of visits to matrix A will become half of k. In MPK computation, dense vectors are typically stored in a separate array of length n. FVMPK visits the same position of 2 vectors in a row to update the later vector. However, the 2 vectors are physically stored independently. And to enhance locality, we merge these two vectors into a single area of length 2n, but they are still separated logically. The two vectors are stored interleaved in vector x, y. When parallelizing the kernel, data dependence must be addressed. For instance, this figure shows the potential dependence that can occur when multiple threads access submatrix L and vector X. If thread 4 completes the computation of this green element first, it will proceed to compute this yellow element of XL2. However, as threads 0 and 1 may not have finished calculating these two gray elements in XL1, obviously, elements 4 and 5 need these two gray elements. A synchronization point must be inserted to pause thread 4 until other parallel threads complete their work. Our approach to parallelizing FBMPK involves using the ABMC algorithm to rearrange the matrix elements. The algorithm organizes the matrix elements into blocks and uses coloring to indicate dependencies. So blocks with the same color can be processed simultaneously. And experiment. This figure reports the speed up achieved by our FBMPK approach over the baseline FMPK on 4 platforms when power k equals 5. FBMPK delivers notable speed ups for most input matrices. Our method achieves 1.5 times, 1.554 times, 1.47 times, and 1.73 times speed up on the 4 platforms compared to the baseline. Matrix Kant shows performance variance between ARM and Intel platforms because Kant has the smallest dimension among all input data. As a result, the computation workload of this matrix is too small to cover the thread overhead after ABMC reordering when using all 64 physical cores. We also measure the total amount of data read and write from DRAM. We conduct this experiment on the Intel Xeon platform and compare our approach with the MKO library. When the power is increased from 3 to 9, the average memory access compared to the benchmark experiment drops from 74% to 62%. We also found that the decrease in memory access is directly related to the sparsity of the matrix. Usually, denser matrices perform better. And recall that we use ABMC algorithm to reorder the sparse matrix to expose parallelism. It may affect the performance of a single SPMV invocation due to the restructured sparse matrix. We compare the time consumption of SPMV before and after matrix reordering. For most of the matrices, we observe little impact. Vector optimization provides additional performance improvement on 13 input matrices on FT2000+. Moreover, the performance benefit of BTB is transferable to the remaining 2 ARM platforms, yielding a 10% additional speed up. We also analyze the impact of SPMV invocations and the pre-processing overhead and so on. Please see these details in our paper. And conclusion. We have presented a new way to optimize multiple invocations of sparse matrix vector multiplication. This computation pattern can be widely found in scientific workloads, but is largely ignored in prior work for SPMV optimization. Our approach reduces the memory access latency of the workload by exploiting the data locality of sparse matrix and dense vector involved in the computation. Experimental results show that our approach significantly outperforming the Intel MKO library, delivering a speed up of up to 2.32 times. Okay, that's all. We open source our code on GitHub. If you have any questions, please contact us. Thank you.